This is section 15.9, and that is using proton NMR spectroscopy to distinguish compounds. So one way that we can use proton NMR to distinguish between similar molecules is by using the number of signals that we observe in the spectrum. This depends on how many protons are homotopic with each other. And you can see a very good example here at the top of this section, where we can distinguish between the isomers of dimethylbenzene simply by looking at how many signals are present. For instance, in the first one, the 1,2 substitution pattern is confirmed by the 3 signals that we observe because only two of the protons in the benzene ring are homotopic with each other. In the second example, with the 1,3 substitution pattern, we can see that there are 3 protons, or 4 protons in total, and 3 benzene ring signals to go with one CH3 signal to give us a total of 4. Whereas in the third example, the 1,4 substitution pattern is confirmed by there being only 2 total signals because each of the benzene rings is homotopic. There's a plane of symmetry that goes right down the middle of the molecule. Another way that we can use proton NMR to distinguish between compounds is shown here in this little example. In these 2 molecules, we're tasked with using NMR spectroscopy to distinguish between the molecules. However, it might seem a little complicated because in both cases, we expect 4 signals from 1, 2, 3, 4. In the second molecule, 1, 2, 3, 4. So there are 4 in both. But what we have to look at is actually the nature of each of these molecules and the chemical shifts that we observe, as well as the multiplicity of those signals. Because in the first one, you expect a peak around 4, around 4 for this proton and around 2 for this one. And so in the signal here around 2, you expect that to be a triplet because of the neighbor having a doublet. But in this example, the signal around 4, you expect to be a singlet because there's no protons on the nearest neighbor. Whereas in the second molecule, you have a singlet at around 2 and a triplet around 4. So that can tell you the relative placement of these 2 CH3 groups here. And that can be a very good way to look at NMR spectroscopy. And in fact, as organic chemists, we use NMR in both of these ways very regularly because NMR is a very powerful tool for distinguishing between closely related compounds. And this has been section 15.9.